Good morning, dear students. Today I am going to discuss about Heap Sort algorithm. Okay. Now, before discussing Heap Sort algorithm, we will discuss about what is heap, and then how you make a heap, and then how we proceed for a heap sort. See, what is a heap? Actually, heap is a type of tree, type of binary tree. And first of all, we will discuss about what is a binary tree. See, a binary tree, as you know, a tree having two nodes, and a fully binary tree is a binary tree in which each node is either a leaf or has exactly two children. See, in this figure, this is a binary tree. In this figure, see, this is a binary tree. This is a binary tree where what happens? Each node is either a leaf. Here 12 is a leaf, 7, 8, 14, 10 and 9. They are leaves. And here 2, 16, 1, 3 and 4. These are 5 what is non-leaf nodes, and remember that those non-leaf nodes are there, they have exactly two children. If this condition is satisfying, then we call it as a full binary tree. Full binary tree. Next one definition is complete binary tree. A binary tree in which all the leaves are on the same level and have internal nodes have degree 2. That means a completely binary tree is a binary tree whose leaves are on the same level, whose leaves are on the same level and all internal nodes have degree 2. You see, this is a leaf, this is a binary tree, and it is a completely binary tree. It is a completely binary tree. Okay, that means a completely binary tree is a binary tree whose leaves are at the same level. You see, in case of full binary tree, the leaves are not in same level, they may be in different level. But all the non-leaf nodes will have exactly two children. But in a completely binary tree, all the non-leaf nodes will have two children. But all the leaf nodes are at the same level. Now, a full binary tree becomes a completely binary tree if the non-leaf nodes which are present not at the same level, that means which are present not at the last level, if you will give two children to each, then it will become a completely binary tree. Okay. Now, what is height of a node? Height of a node means the number of edges on the longest path from the node down to leaf, from the node down to leaf. That is okay. Height of a node. Height of a node means, see, in this case, the height of a node means that means the longest path from the node down to the leaf. See, in this case, the height. In this case, you see, in this case, this node height is what is the longest path to reach the leaf. See, to reach the leaf, it has to travel one path. To reach the leaf, it has to travel one path. Hence, the height of this node to this node is 1. The height of this node is 1. Now, the height of this node is 0. The height of this node, because it is already a leaf, hence height of a node is 0. Height of a leaf node is 0. Now, label of a node. The length of a path from the root to the node is called label of the node. What is the label of a node? The length of the path from root to the node. See, what is this label? What is the label of this node 10? See, from the root to this node, how many edges will be there? How many path length will be there? This is one path, this is two path. Hence, label of this node is 2. Similarly, label of this node is also 2. Label of this node 8. Label of this node 8 is also not 2, it is 3. See, 1, 2 and 3, because from root node to reach to the node 8, root to 8, it has a travel height is 3 paths. Hence, the level of this node 8 is 3, and height of a tree. Then height of a tree. Height of a tree is nothing but height of the root node. Height of the root node means, height of a node means the longest path from this node to the leaf. Hence, from the height of this node means from the root, what is the longest path? This path is not longest. This path is longest to the reach to this leaf or to this leaf. Hence, 1, 2, 3. The height of this node is 3. Okay. Hence, height of tree is the height of root node. Level of a node means from the root to that node is the level of the node. The path from the root to that node is called the level of node. And the height of a node means from this node to reach the leaf node, highest path to the leaf node. Any leaf node which is present at the highest path, that is called the level of this height of this node. And a height of the root node is nothing but a height of a tree. Now, some useful if there are at most 2 to the L nodes at level L of a binary tree. If there is a binary tree, then at a particular level, how many nodes will be there? 2 to the power L nodes. 2 to the power L nodes. What it is saying? You see, at a particular level L, 2 to the power L nodes will be there. 2 to the power L nodes will be there. See, in this level, how many nodes are there? This level? At most 2 to the power L. 2 to the power L nodes will be there, which is equal to, what is the level of this node? What is the level of this node? You see, from root to reach here. What is? 1, 2. Hence, it will be 2 to the power 2, which is equal to, because level of this node 10 is 2, level of hence how many nodes? Max. That is 2 to the power L, 2 to the 2, that means 4. That means in this level 4 nodes are there, because level of this node is 2, hence in this level 4 nodes are, and in this level how many nodes are there? See, this is 1 node, this is 2 node, this is 3 node, this is 4 node. Hence in the level 2, 4 nodes are there. At most 4 nodes will be there. Hence in in this level how many nodes are there? You see, in this level how many nodes are there? What is the level of this? What is the level of these nodes? Now this is, you see, from root to this node, it is hence its level L is equal to 1. Hence number of nodes will be 2 to the power L, which is equal to 2 to the power 1, which is equal to 2. Hence 2 nodes, that is this node and this node. And 2 nodes are there in the level. See, a binary tree with height, next one, a binary tree with height d has most to the power d plus 1 minus 1 nodes. What is it saying? A binary tree with height d, a binary tree with height d has at most 2 to the power d plus 1, 2 to the power d plus 1 minus 1 nodes. You see, how can you see that? See, suppose there are, it is proving that, suppose there are n nodes, see, in each level how many nodes are there? See, in each level, because in a binary tree of height d, see, in this case, what is the height of this node? Height of this node is 3. Height of this node is 3. In this binary tree, how many nodes will be there? 2 to the power 3 plus 1 minus 1. That is man 2 to the power 4 minus 1. That means 2 to the power 4. 2 to the power 4 means there is only 2 into 2, 4, 4 into 4, 16, 16 minus 1. That means 15 nodes. At most 15 nodes will be there. But here how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes are there. But if you add 2 nodes in each, this also can be in the same height. Hence 2 to, that means if you add this, you see, if you add this can be a binary tree of the same height. Hence how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15 nodes. Okay, that means exactly 15 nodes will be there. 15 nodes will be there. Okay, now my question is that how it is happening? It is, see, here it is proving like this. See, in a particular level, how many nodes will be there? That is your 2 to the power 2 to the power L nodes will be there, and what will the level? Level will be from 0 to D. That means which is equal to 2 to the power D plus 1 minus 1 divided by 2 to the power 2 minus 1, as it is proving, which is equal to 2 to the power 2D plus 1 minus 1. This number of nodes will be there. See, a binary tree with n nodes has height at least log n. At least log n. See, a binary tree with n nodes has height at least log n. Remember that. A binary tree with n nodes has height at least log n. In this case, what is the n value? N value is 15. If you complete all these things, hence it will be, what is the n value will rise? In this case, see, in this case, at height 3, how many possible at height 3? Say in this case at height 3, how many possible nodes are there? At height 3, the possible nodes will be, n value will be from 1, 2, 3, 4, 5, 6, 7, 8. From 8 to 15 will be there. N value can be 15. If we are erasing this node, then this also will be a binary tree having 2 to the power at most, that is 2 to the D plus 1 minus 1 nodes. That means 8 to 15. 8 to 15. That means 8 to 15. And in this case, if there is 8, then 8, then log 8 will be 3. That means height 3. If 15, log 15 is equal to, that means the lower bound of log floor of log 15 is equal to also 3. Okay, that means floor of log 8 is equal to 3, and floor of log 8 is equal to 3, and floor of log 15 is equal to 3. That means any, if we have n nodes, if we have n nodes, then height will be at least log n, at least log n, floor of log n, and that can be proved also. That can be proved also. Okay. Now next, the heap, a data structure. See, a heap is a nearly complete binary tree. What it is saying? A heap is a nearly complete binary tree. See, a heap is a nearly complete binary tree. Nearly complete binary tree. What is it? Nearly complete binary tree? We have discussed about two things: fully binary tree and complete binary tree. And nearly complete binary tree means, actually nearly complete binary tree is defined as like this: all leaves are full except possibly the last one, which is filled from the left to right. See, a nearly complete binary tree, that means it is a completely binary tree. Suppose there is we say a binary tree is heap. A binary tree is heap if at it is a full binary, it is a complete binary tree up to level L minus 1, up to level L minus 1. Up to level L minus 1, it is a, that means from the root to L minus 1 up to this, it is a completely binary tree. And the last level, it is filled from left towards right. It is filled from left towards right, except possibly the last one, which is filled from left to right. And along with it, it is also satisfied another property. For any node x, parent of x is greater than x. That means parent of x. Parent of x means the value of a parent of x is always greater than x. That means the value of parent is greater than equal to the value of child. Then if these two properties is satisfying, we call it as a heap. Rather, we call it as a max heap. If value of parent is less than equal to x, if value of parent is less than equal to x, then in that case we call it as a mean heap. But what is a heap? Heap is a, first of all, it is a completely binary tree up to level L minus 1, and at the last level the nodes are filled from the left to right. And along with it, either it can satisfy the max property, this property, or the mean property, that means less than equal to x, this property. Then it is called, if this is satisfying this property along with the first property, then it is called a max heap. If it is satisfying the second property along with the first property, the second one, along with the first property, this property, then it is called a mean heap. Okay. Now, see how we can thought as about, see. Okay. See, any array is given, first of all, we can think at it as a nearly what is complete binary tree. Nearly complete binary tree. See, if this is the node, then first element will be the root, the second two element will be the its child, and next two will be that means this one's child is up to this one child is these two, and this one child is these two, and this one child is these two, and this one child is only this one. If there will be another one, this one will be there. And in this way, we can think at it as a what is nearly complete binary tree. Nearly complete binary tree. Say any array is given. Suppose I am giving another example. Suppose the element is there. Suppose I am giving 2, 3, 9, 17, 10, 15. Suppose this array is given, then this array, if this array is given, then this is also thought as a almost completely binary tree. That means the first node, root node will be 2, then its left child will be 3, its right child will be 9, and 3's left child will be 17, and right child will be 10, and its left child will be 15. Okay. Now see, this is a given array of 6 elements. Now this 6 element can be thought as almost completely binary tree. Sorry, nearly completely binary tree. This theta thought as nearly complete binary tree. Hence, any array is given, it can be thought as a nearly complete binary tree. Nearly complete binary tree, as it is happened. Nearly complete binary tree. Now this is also a nearly complete binary tree, but this becomes a heap since it is satisfying the heap property. Hence, first of all, any array is given, it can be think as a nearly complete binary tree. And once you will check if they are satisfying the heap property, then it will be a heap. Okay. Now for the nearly complete binary tree, root will be a1, and what is the left child ai will be a2i, and right child ai will be a2i plus 1, and parent of I is equal to ai by 2. And heap size in this case, if it is satisfying the heap property, then heap size you will calculate This is the heap size. Okay, max heap means, as I have already told, the max heap is nothing but if the parent value is already greater than equal to its child value, and mean heap if parent value is less than equal to its child value. Now, adding and deleting a node in a heap. See, adding, if you want to add a node, we will always add a node there in the last node. We will add in the last, and you may move this node if it is not satisfying the heap property. We will move the node accordingly. Okay, suppose you want to delete a node. Suppose a particular node, this one will be deleted. Suppose it is 25 here. You have already added, and you want to delete it. Then these two nodes will be exchanged, and this one will be deleted. This is the deleting or adding process in a heap. Now, operation on heap. Operation on heap is first of all heapify. Heapify, that means maintaining the heap property or restoring the heap property is called heapify. And if you are restoring the max heap property, it is called max heapify. If you are restoring the mean heap property, it is called mean heapify. And restoring or maintaining the heap property is called heapify. And if you are returning the max heap property, then it is called max heapify. If you are returning mean heap property, it is called a mean heapify. Build a heap, build a max heap. If you are building a max heap, then it is called build max heap. If you are maintaining or building a mean heap, it is called a mean heap. See, once an array is given, it can be thought as a nearly complete binary tree. Nearly complete binary tree, but it may not be a heap, but you have to make a heap. And then we will discuss another algorithm called heap sort algorithm. Priority we will not discuss in the class. These three algorithms we will discuss. What is max heapify, build heap, and heap sort. These three algorithms we will discuss in the class. See, maintaining heap property. Heapifying, maintaining heap property. Suppose this is what is nearly complete binary tree is given. Nearly complete binary tree is given. Then we want to maintain the heap property. Maintain the heap property. See, this case the heap property is maintained, and this case is heap property is maintained. See, the leaf nodes is by default the heap property is maintained. But the non-leaf nodes, you have to check whether the heap property is maintained or not. See, for this the heap property is maintained. Here we are considering about max heap, and the max heap property is maintained because this parent value is greater than equal to the child value. In this case, the parent value is greater than equal to the child value. But you see, this case, the parent value is not greater than equal to the child value, because parent value is 4, child value just one is 14, another is 7. Hence, this is violating the heap property. Hence, but maintaining the heap property is called heapify. It's called heapify. Now, in this case, what will happen? 14, 7. Then which one is the bigger? They will go to the root. Hence, out of these three, 14 is bigger. Hence, 14 will go to here, 14 will go to here, and 4 will go to here. Now, in this case, again, we have to, because once we are taking 4, this is also violating the heap property. This is violating the heap property. Hence, for this case, because we have violated the heap property by making a smaller, and we have to check, no, 4 to 8. 8 is bigger, hence we have to exchange here. Hence, exchange here means instead of 4, we have to write here 8, and instead of 8, we are writing 4. Now you see, now 8 is satisfying the and this one. Hence now it becomes a heap. This process of is called heapify, because this is violating the heap property. It has to move down either left node or right node, depending which one is the bigger, and we have to exchange it. If then again we have to check whether it is heap property is maintained or not. Accordingly, we have to move, and that is called heapify. See, heapify, that means here what is in the previous case, what is there, we are just heapify. That is called max heapify, because you are maintaining max heap property or mark, and that we have done for the heapify. A 2 because the index of this array is 2, or index of this position is 2 because 1, this position is 2, because you see, if this is the array we are considering, see what is 16, then 4, then 10, then 14, then 7, 9, 3, 2, 8, 1. If this is the case, this index is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements are there, and you see by this can be think as what is nearly complete binary tree, but in this case all see this node is satisfying heap property, this node is satisfying heap property, this node is satisfying heap property, but this node is also satisfying heap property, but this node is not satisfying heap property. Hence we have to since this node is not satisfying heap property, we have to maintain the heap property, and that is called heapify. And in this case max heap property we are satisfying, hence it is a. 2 means the index of this element which is not maintaining the heap property, and what is 10? 10 is the heap size. 10 is the heap size, because this is you are maintaining, if you are making it heap, then heap size is all the elements present in the heap, that is heap size, and it is 10 elements are present. Now in this case what happened, as I have already told, 14 will go to here and 4 will go to here. That means here it will be 14 and here will be 4. Now in this case what will happen? Again in this case what is it? The heap property is violating, because here A2 is violating heap property, and then again what is, if you will do this, exchange will be A2 with A14, A4 will be, because of A4 this is A2, because the R index is 2 here, R index is 4 here. A2 is exchanged here with what is A4. Now doing this, again this violates the heap property, hence what will happen, again we have to, A4 violates the heap property, again we have to call what is max heapify A, because again we have to call here max heapify what is A here 4 and 10. Again we have to call, so that only we can do the exchange. Okay, now here 8. Now in this case here what happens, the heap property is restored. That process is called heapify. Now this what we have discussed in this case, how to heapify, this is discussed here. What is max heapify? Max heapify means what happen? First of all, how it is happening? You see how it is happening. First of all, if it is I, see if it is I, if this index is I, here I is 2, I, then this and this, that means 2i and 2i plus 1. This indicates that 2i and this indicates 2i plus 1, because 2i means 4 and 2i plus 1 means 5. That means this indicates 2i indicates the left array and 2i plus 1 indicates the right array. And along these three elements we are comparing the array I, array 2i and array 2i plus 1. And which one is the bigger? They will be exchanged with I. If the I becomes the bigger, no need to extend and terminate there. You see this is happening. See what is happening here. L is equal to left of I, R is equal to right of I. What is left of I? As we have already told, left of I is nothing but 2i. We have already defined what is left of I, and right of I is nothing but 2i plus 1. Right of I. Now if L is less than L, if left of I is less than N, N means heap size. If it is exceeding the heap size, that means no element is there, no need to compare. And AL is greater than AI. If left of A, left of this element is greater than the I value, that means AL becomes the largest, hence we are largest will be AL, otherwise largest will be I. That means in this case what is happening, we are comparing the left element. See this is the element, see that means this is I, this is 2i and this is 2i plus 1 index. Now these two elements we are comparing, this element and this element we are comparing. If this one is the largest, 2i is the largest, left is that is 2i, because L is equal to 2i and R is equal to 2i plus 1. If this is the L is the largest, then largest will be L, and if similarly if R is not beyond the size of the heap, then it will be compared with the A largest. If this one is the largest, then this value element and this element will compare. If this one is the largest, then this element and this element will be compared. Then largest accordingly will be done. If largest is not equal to I, if this is the I, if its value is not largest, then someone here or someone here will be the largest, and there will be the exchange AI with A largest. After doing this, then max besides A largest. And it happens here. You see what is happening here. Heapifying. See what is happening here. You see this is, we are heapifying this I. This is 2I, and this is 2I plus 1. Now among which one is the largest? Largest is equal to in this 3, largest is equal to 2I. Now then what will happen? Then we will exchange largest with AI with A largest, and then what is become, this 4 becomes here largest, hence you are A for violet. That means again we are calling heapify A largest, then N. This again we are calling here, then that means again it is coming. That means again these two are comparing. Hence this is the scenario. That means if you are doing the heapify of a particular AI, then its left child and its right child will be compared, and if the largest is not in the I, then there will be exchange. Which one is the largest will be taken place. Again we have to heapify this. This is the heapify algorithm. Now let us calculate the time complexity of this algorithm. Now it is saying the running time of max heapify is log n. The running time of max heapify is log n. See how we will calculate the running time of this heap sort algorithm. Let Tn be the running time of this max heapify with index I. Then Tn will be, what is, this is a constant time, 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 and this is a constant time, this is also a constant time. That is, I can write C, all constant together, I can say C plus this same max heapify. If this is Tn with I, then Tn with largest, that means the largest value of largest number of elements. Suppose this is Tn. Now this is going to here with T largest. Remember that this largest, see this tree, if you are making this tree contains this number of elements. Once it is coming to this subtree, it contains only this number of elements. Hence Tn is equal to C T. The size of this, that means you will be 2n by 3. Why I am writing 2n by 3? I am explaining. See, suppose where I is pointing, that tree, subtree where I is the I is pointing to a node which is a root node. The number of element is, if it is n, then it is going either from the left child or the right child. That means the left subtree or the right subtree. The number of node in the left subtree or the right subtree will be at most 2n by 3. What I am saying, that means Tn. Tn means what is n? Number of elements in the tree whose node is I, whose root node is I. Tn is, what is n? N is the number of element of the tree whose node is at I. If this is the n, then what is the number of elements where the largest is pointing? Largest may point to the left child or it may point to the right child. If it is the case, how many elements there where the root is the pointing to the node of the largest, means the largest index, then in that case it will be at most 2n by 3. 2n by 3. How it is 2n by 3? You can count. See, you see, in a see, in this case, see, suppose we will cut this node. See, up to this, how many elements will there? Up to this, it will be, see, number of elements here is, okay, I will explain this later, how it is 2n by 3, but remember that, and Tn is equal to C plus 2t into 2Tn plus 3, remember that, That means in a node, in a what is in a nearly complete binary tree, the subtree, the node of the number of elements present in a particular tree and the number of elements present in a any of the subtree is, if it is present in the node, if the tree it is present n nodes, in the left subtree or right subtree, how many nodes will be present? Then it will be 2n by 3. And remember that this is a recurrence relation, we will come in this point later, and you will solve this recurrence relation. You will see that Tn will be your what is it will be big O of log n. In this case, okay, that means Tn is C plus T 2n by 3, and in this case you will solve this, and later we will solve Tn is equal to big O of log n, big O of log n. This thing we will prove, but remember that if there is a binary tree, a nearly complete binary tree where Tn is the number of elements of at a root, then the number of elements of a subtree whose root may be either left node or root may be at the right node will be, number of element will be 2n by 3. See, build marks heap. See, build marks heap. See, suppose we have given the nodes 4, 1, 3, 2, 69, 10, 14, 8, and here 7 is written. After 8, 7 is written here. After 8, 7 is written here. Okay, if this is a array is given, if this array is given, then we can think it as a nearly complete binary tree. Then, but this is not a heap, that is not a max heap. Hence, what will happen? We have to build max heap. In order to build max heap from right towards the left up to the tree. That means first this, then this, then this, then this, then this. What happens? We have to heapify, max heapify this, and once we will do the max heapify, then it will be what is we will build a heap. Hence, what is happening here? N is equal to length of A. Length of A is n. What is n? N is the heap size. And for I is equal to n by 2 down to 1. See, in this case, only n by 2 elements will have the child. See, this 5. Here 10 elements, 6th index array element has no child. Only 5th element index has child 16, which is 7. Has child, and that is 16, has child 7, and its index is 5. Hence, because from the properties of the tree, it is clear that only n by 2, out of n, only n by 2 elements will have child. Hence, from n by 2 down to 1 means up to this, we have to max heapify ai1. We have already know how to max heapify, and will be max heapify ain. If you will do this, that means if you will, what is, if you will max heapify this, max heapify this, max heapify this, max heapify this, then max heapify this, because I will be n by 2 down to 1, I will be 5, I will be 4, I will be 3, I will be 2, I will be 1. If we max heapify this, then we will build a heap. Okay, we will build a heap. See, let us consider this. In this case, you see, in this case, what is happening? This is first of all 5. We have to, according to algorithm, we have to heapify this. You have to heapify this. Then you have to heapify 3 in position. You have to heapify 2 array index. Then you have to condition heapify IR index, because you see here what is happening. Here what is happening? I is equal to n by 2 down to 1. That means 5 up to 4. Hence, what is the n? N is equal to 10. Hence, I is equal to, first in this case, I is equal to 5. Hence, if you heapify this is 16, 16 is greater than 70. It is satisfying heap property. Hence, heapify will do nothing. Next will be I will be 4. In this case, if I will be 4 means what will happen? In this one, see, this one is you want to heapify, which one will come? 14 will come here and 2 will come here. That means 2 you will write here and 14 will be right here. And by default it is heapified. Hence, next what will happen? I is equal to 3. I is equal to 3. 3 means this. You have to max heapify. Max heapify means in this 3, which one is the bigger? 10 is bigger. Then 10 will go to here and 3 will go to here. 10 will go to here, 3 will go to here. Then I will be 2. I will be 2 means you have to heapify 2 index element. That means out of these 3, which one is bigger? 16 is bigger. Then 16 will go to here, 1 will go to here. And now here 1 is there. Now 1 and 7, that means 7 will go to here and 1 will go to. That means here it will be 1, here it will be 7 and here it will be 16. 16. Okay, that means this 16. Hence what happens? 16, 17. Now I will be 1 and once I will be 1, you have to heapify this. That means out of this 4 will 16 will go to here. Now here it is 4, but 4 and 14 and 7, which one is bigger? That means here it will 4 will come here, but out of 4, 17. It is not satisfying the heap property. Again what will happen? 14 will go to here and 4 will go to here. That means 14 will be here. Instead of 4, you have to write 14 here. Now here what happened? 4 to 8. That means 2 will go to here and 4 will go to here. That means here it is 4 and here it is 8 instead of 4. Hence, next what will happen? You see, that means 14 has gone to here, 16 has gone to here, 14 has gone to here, then 8 has gone to here, then 4 has gone to here. And now this is a what is max heap. That means you are building a heap by what is happening from starting from I by 2 towards I is equal to 1 and heapifying each are a index. Each are a index. Okay, this is the now. Okay, this build heap. Now we will consider what is the running time of build max heap. That the running time of the running time of build max heap is n log n. N log n. How we will prove this? How we will prove that the running time of build max heap is n log n? Let us check. See, as you know, heapify takes big of h, big of log n or big of h. See, as I have already told that heapify takes big of h or is equal to log of log n. Big of log n. Log n means see log n. Now see or big of h and big of if n elements are there, then height will be if n elements will be there, then the height of the tree is having n elements is h. Hence big of log n is same as big of h. Remember, big of log n is same as big of h. Hence, if the build max heap, let the build max heap is the time complexity of build max heap is Tn. Then Tn is equal to what? Big of h is what we can write is what we can write? Big of h is nothing but c into h. Big of h is nothing but c into h. You can write. Now, in this case, if the time complexity of build max heap is Tn, then it will be what is? We will build the max heap if from the that is from this, all these things. What happens? We have to the heapify algorithm. So we have to take consideration. We have heapify algorithm. Hence, it will be I from 0 to h. Height I from 0 to h. 0 to h. Because I from 0 to h, I is equal to 0 to, and summation of h, ni, hi, ni. Because in this, how many nodes are there? In this level, how many nodes are there? That means I am saying at a particular level I, ni nodes are there. Then ni into hi. Of course, there is ci is there. Hence, in this case, what will happen? n, that means how many nodes are there? This is equal to 2 to the power I, 2 to the power 2 to the power I nodes are there, and hi from I is equal to 0 to h, and what is h? H is the height of the tree at a particular root. Hence, in this case, you see, just I am writing, which is equal to t n is equal to, for this case, 2 to the power 0 and height is h, plus, in this case, 2 to the power 1, height will be, if it is h, whatever the height, if it is, we are saying h, then here it will be h minus 1. In this case, and how many elements are there? 2 to the power I, that is 2 elements are, and in this case I can write 2 to the power 2 into h minus 2. Like this I will add, and that will be the Tn, that will be the Tn, and you see, I 2 1 0. Okay, now if you will do, if you will do this like this, you see, if you will do like this, cost of this particular is the cost of Heap. This one is the cost of Heap, is value I. Then what will happen? Using following the formula, summation of I to the I, hi minus 1 is equal to this formula. You see, h minus I divided by 2 to the power h minus I into 2 to the power h, and 2 to the power h we take in its constant, it is equal to k by 2 to the power k from 0 to h. Okay, because h minus I we consider as k, hence k is equal to 0 to, change the variable from h minus I to k, hence it will be 2 to the power h. 2 to the power h is nothing but number of nodes. If h is the height, 2 to the power h is the number of nodes n, and then it is equal to k by 2 to the power k from 0 to infinity. Just it is less than equal to, because we have added infinity, hence we make it less than equal to, and 2 to the power h is nothing but k, hence it is equal to big O of n. Hence running time is of build mark ship is big O of n. Now Heap Sort. See, now we are going to Heap Sort. Then what is happening in Heap Sort? You follow the you just first of all we write the algorithm, then we will list. This is the Heap Sort algorithm. You see, Heap Sort algorithm, first of all build mark ship. We know how to build mark ship. We have already discussed the algorithm. For I from length of a down to 2, from I length of a down to 2, do exchange A1 with AI, then mark ship A1 I minus 1. I minus 1. Okay, see what is happening here. See how the heapify is happening. See, once you are building a mark sheet, the top element, see, once you are building a mark sheet, see, here you have, in this case, see, this is a mark sheet you have built. Now, once you are building a mark sheet, the biggest element is at the what is first array index of the array, first array index. If you arrange this, see, this one will be 16, then 14, then 10, like this it will come, like this will come 10, then it will come 8, then it will come 7, then it will come 9, like this. See, the array, if you will build a mark sheet, the array is not sorted, but the highest element, the biggest element is at the top of the, what is at the first array index of the in the first array index. Hence, in a sorting, this element has to go to the at the end. Hence, what will happen? You delete this element. As I have told in the heap, to delete the element, you have to exchange with the last element. You have to exchange this element. You have to exchange this element with the last element. You exchange this element, that means this element with the last element, and this element with this last element. And after doing this, just delete it. After deleting it, and this element now, because here 7 will come and 16 will come to here. See here what is happening. I am again doing the thing. See here what is happening. 16, 14, 10, 8, 7, 9, 2, 8, 1. Okay, that means here what is this element? Here it is 3 is present. In this case 3 is present. No, 1 is present, the last element. Now what happened? You in this case, the last element, this index element and they two will be interchanged. That means here what is happening is 1 will come, here 16 will come. Okay, now you in the heap, you don't consider this as the member of the heap. That means heap size will be decreased by 1. Now what happened? This one will be 1 and this one will be 16, and this connection will be turned down. That means heap size will be decreased by 1. Now doing this, everyone is satisfying the heap property except this. Hence what will happen? Heapify. Then you will call heapify with the first R index. Heapify this, because this is instead of 16, now this becomes 1. Hence what heapify 1. Then 14 will go to here. Then 8 will go to here. Then 4 will go to here. That means 14 will go to here. 8 will go to here, and 4 will go to here, and 1 will go to here. That means the new array will be what will be? 14, 8, 10, 4, 7, 9, 3, 2, 1, and here 16 is there, but it is not considered. Now again what happened? This 4 and 1 will be interchanged. 4, 1, and it will be 14, and this one will be out of this heap, and again we have to heapify this. Now doing this, that means first of all what we will do? We will do build max heap. Then for length, length of a down to 2. That means from length of a initiality n down to 2 means leaving the last element down to up to 2, not the last element. Exchange a1 with ai and max heapify a1 with I minus 1. We are decreasing the heap size by 1, I minus 1. Okay, I minus 1, and doing this you will sort the algorithm. Let us consider the example. Suppose this array is given, or this heap is given. In fact, this heap is given. You see, in this heap, what we will do? We will exchange this. Exchange this means, because if you will do this heap, you see what is the array position is. Array is like this. Now what will happen? 2 will be exchanged with this. That means this one will go to the here, and this one will go to here. That means what happens? And max heapify A1 4 because previously it was 5, now it is be I minus 1 4. Hence what will happen? That means next it will what happen? This 7 we have not considered inside the heap. Now this is our heap, and in this is again we have to do exchange this with this and heapify. What's happening? Heapify. After heapifying, 3 will go to here, 4 okay. Heapifying this will happen and 2 1 will consider. That means we will again what happen? We will cut this one is the out of a heap. Now this one will happen. Hence what will happen? Again we will exchange this with this exchange, and doing this then we will heapify. That means we will out of this, then we will heapify. Then 1 2 heapify. Then that means now if you are doing this, what happen? 7 4 3 2 1. Now what will the my new array will be? You see, it is in the array, but we have just not included that. First is 7 at the end, last end, then 4, then 3, then 2, then 1. Okay, now it is sorted, and this is the way the array is sorted. And what is the time complexity of this algorithm? Now build heap will take, as we have already told, that build heap its time complexity big of n, and for A1 length one, how many times it will be run? It is n minus 1 time it will run. And what is heapify? Log n. That means it is big of n log n, big of n log n, because n minus 1 times the log n will run. That means big of log n. Hence heap sort algorithm runs big of n log n, and it can be also shown that it is theta of n log n. We have calculated big of n log n, but can be shown that it is theta of n log n. Hence, irrespective of the average case, worst case, or best case, your heap sort algorithm will take theta or big of n log n. Okay, now we are stopping the class here.